Okay, so as I am doing the series of analysis videos on elastic collisions, I'm also going to be doing a series on explosion experiments. And I'm going to do this mainly because of the following claim by Draft Science. I'm going to play the clip where he explains his argument. This was in response to a comment of physicist Michael.
Totally ignored it. You just, and it's just so dishonest, so bullshit. I mean, I made it as clear as I can possibly make it that you're not talking about the same thing. You cannot call it conservation of momentum. All right, when we know the spring has stored something, okay, it stores something. All right, and whether it's kinetic energy or it's momentum, you have to say it stores something called energy. That's what the spring does. So here he has an experiment. All right, he's telling me this is not paradoxical or strange or unbelievable. All right, one mass, two mass. Same exact spring compression. So I put the same amount of force into the spring. Same force here as here. Okay, same identical force is in the spring. And I get twice the momentum here. I get 200. All right, so these leave with 200 momentum and 200 momentum over here, and only 100 here, and only 100 here. So you have a total of 200 momentum from the spring, same force you put in, and you have 400 out here. Okay, same exact spring compression. And he says that's conservation of energy. How can it possibly be conservation of energy? I put in 1 unit of force, whatever this force unit is, and somehow I get either 2 units of energy out, or 1 energy out, or I can get a half, or I can get 4. So I just make these things bigger and bigger, and I get more and more momentum. I make these things smaller and smaller, I get less and less momentum. And he's saying I shouldn't have some kind of disagreement with that logic. I should say it shouldn't be possible for me to say, how is this conservation of momentum?
Okay, so we get it by now. So as I understand it correctly, what you mean is we have a spring. So we have an explosion. The spring creates a certain amount of energy, and that's the amount of energy that should always be conserved. It can possibly create more energy when we change the masses. The spring always has a maximum amount of capacity to produce energy. So in this case, indeed, when let's say we put a 10 mass over here and 10 mass over here, and then the spring releases its energy, and let's say that the 10 mass goes 10 meters per second, and this one also 10 meters per second. Momentum of this one is 100. Momentum of this one is 100. Now, since draft science, according to draft science, momentum is energy, and so momentum is a scalar in his theory, which means we have to add both momentums. So it will be 200 momentums, and that will be the energy. And so when we are going to change the masses, so let's say a 20 mass versus a 20 mass, and we release the spring again in another explosion, that means that this card will travel with a velocity of 5 meters per second, because 5 times 20 is 100, and this one also 5 meters per second. So we get a 100 over here and a 100 over here equals 200. So which was the same as the initial momentum. So if the initial momentum is 200, that's the maximum amount of energy. And so no matter what the masses are, if we're going to continue to change the masses, it should always produce 200 momentums, according to the draft science theory. Now, unfortunately for you, there's not a single experiment that verifies these predictions. Okay, I've been analyzing a couple of them by now, and not a single one produces this constant momentum. It does produce a constant kinetic energy. That remains the same, that is conserved. Momentum always changes if we change the masses. Now, according to mainstream science, the momentum here and the momentum here is always going to be 50-50. Even though if they are unequal masses, we can have a 5 mass over here and a 10 mass over here, or a 50 mass over here and a 3 mass over here. If the explosion happens, the momentum here and here will always be the same. And since mainstream science treats momentum as a vector, which means that when one card goes the opposite way, it will become a negative, all right? So with an explosion, it's 50-50. You got plus 50 and minus 50, and when you add those, it will equal 0. And in that way, momentum is always going to be conserved. Now, I'm going to prove this with an analysis that I have made of one experiment. I will do one experiment per video, as usual. So we're going to look at this one. I'm going to spare you some time. So what it's going to do, so you can see here, a passcode is I've analyzed some other elastic collisions of the same person. Is going to start with equal masses, 270 grams versus 270 grams, and then is going to add weights of 250 grams onto the blue card. So we have a red card and a blue card. The red card will stay the same, always 270 grams. The blue card will, each time, in each run, its mass will be increased by 250 grams. As you can see, 270, in the next test, it will be 520, and the next test, 770, 1020, and 1207. So there are going to be 5 trials, and at the final trial, the blue card is going to be 1 kilogram heavier. So I've written down all the data and done the calculations, the momentum and the kinetic energy. So in the first trial, we have 270 grams versus 270 grams. The velocities being produced, you can check it out, and we'll put the link of the experiment in the description. I'm not going to follow the video. I'm not going to play a video. It's going to cost too much time. But I can tell you that the data is correct. You can verify for yourself. Just check out the video. So 270 versus 270. Velocities after explosion are 8.850 meters per second and 847 meters per second. Little change, but it should theoretically be exactly the same. And therefore, the momentum, this and this side and this side will be exactly the same. And the momentum is minus 0.2295 and plus 0.2287. Slight difference, but theoretically, since it's a vector, minus 0.22 plus 0.22 equals 0. Momentum is conserved. According to draft science, he would say, no, we have to add those together, it's going to be 0.44. So that's, according to draft science, that's going to be the total amount of energy, 0.44 kilograms meters per second, or joules, or whatever. If we use 1/2 mv squared, the kinetic energy is, over here to right, we have 0.097 joules, and for the left card and the right card, the kinetic energy is 0.096. So they're equal, of course, because they have the same mass. And the total energy is 0.1943 joules. So this is the total energy, and this should theoretically remain the same no matter what the masses are going to be. If we are going to change the masses, it should always produce a total kinetic energy of 0.1943. There we go. Now you can follow me better. So let's go to the second trial. The mass is increased by 250 grams. So we have 270 grams versus 520. The result is, after explosion, the velocity is 1.021 meters per second and 0.459 meters per second, which means that the momentum for the red card is minus 0.27, and the momentum for the blue card is 0.23 kilograms per meter second. Yes, kilograms per meter second. We have an increase in momentum because in the first one we had 0.22 and 0.22, and now it's 0.27 versus 0.23. So it's already producing more momentum. So according to that science, more free energy. Because the total amount of momentum here, if we add them together and we treat them as a scalar, positive, 50, around 51 momentum. And in the first one, we had around 45 momentum. So we already have extra momentum. And that should not be, can be true. Now, if we apply the kinetic energy formula, 1/2 mv squared, the red card produces 0.14 joules, the blue card produces 0.05 joules, and the total energy is 0.1954. Now, again, in the first trial, we had a total amount of kinetic energy of 0.1943 joules. And in the second one, 0.1954. A small difference, but energy is pretty much conserved. The kinetic energy. Momentum increases, but look. All right, we have 0.27 versus 0.23. Theoretically, it should also be 0.27 on the other side, such that minus 27 plus 27 would equal 0. We have quite a deviation here, but let's take a look at the next trial. We're going to add another 250 grams, 270 versus 770. Velocity, after the explosion, the velocity is 0.059 meters per second versus 0.358 meters per second. Momentum is 0.28 versus 0.27. Again, the momentum has increased a little bit. The total amount of momentum is bigger than the previous one. All right, so each time if we're going to add weights, the total momentum will become bigger. Well, according to draft science, because we have to add them as they are both positive, as they both have a positive value. But no, according to mainstream physics, the one that goes in opposite direction has a negative value. So we have negative 0.28 versus positive 0.27. It should be exactly the same. It's a slight difference, not too much. So look, the difference is 0.006. That's not much. What is it correct? No, it should be, I think this is wrong. But 0.28 versus 0.27, yeah, not much. So it's pretty much conserved momentum. Now the kinetic energy is for the red card 0.1514 and for the blue card 0.049 joules. So a total kinetic energy of 0.2007. It's a little bit more than the two previous ones. We have 0.19, 0.19, and now we have 0.20. Very small difference. Next trial, we're going to add another 250 grams, 0.270 grams versus 1 kilogram, 20 grams. The velocities are 1.83 meters per second versus 0.275 meters per second, which means the momentum are going to be minus 0.29 versus positive 0.28. Again, a small difference, just difference of 0.0190, small difference. Again, minus 0.29 plus positive, so negative 0.29 plus positive 0.28. Theoretically, it should have been 0. The difference is 0.0190. According to draft science, we have to add them together. We have extra momentum. We have gained more momentum, more energy. When we compare it with the previous one, with the previous one, with the previous one, and with the previous one. So each time when we add weights, we have more momentum, which should not be possible. All right, so the kinetic energy is for the red card, blue card, 0.15 over here and 0.03 over here. A total kinetic energy is 0.19 for the fourth trial. Right, so we have first trial 0.19, that's the total kinetic energy, and then the next trial 0.19, and then the next trial 0.20 and 0.19. So it remains pretty much the same, the kinetic energy. The total amount of energy right now until now is pretty much conserved. Okay, momentum as well, as if we're going to treat it as a negative momentum for the one that goes in opposite direction. Now the last trial, the fifth one, we add another 250 grams. So now we have 270 grams versus 1,270 grams. The velocities are 1.13 meters per second versus 0.22 meters per second. The momentums are negative 0.30 and positive 0.28. Small difference, should have been the same, also 0.30 over here. The difference is 0.0207. Again, if we treat them as a scalar, and both as positive, then we have even more momentum compared with the previous ones. So it keeps increasing as we increase the weights. But if we treat momentum as a negative, as a vector, then we have negative 0.30 plus positive 0.28. Should have been 0, but it's 0.0207. But roughly, there's always a small difference. And the kinetic energy is 0.17 for this side and 0.03 for this side, a total energy of 0.2041 kinetic energy. So now I have put the data next to each other. So the kinetic energy in the first trial is 0.19. In the second trial, it is 0.19. In the third trial, it is 0.20. In the fourth one, it's 0.19. And in the fifth one, it's 0.20. So it's pretty much conserved. I think this experiment has done a good job. Kinetic energy is conserved throughout the 5 trials. Momentum in the first trial is minus 0.22 versus positive 0.22. Momentum is conserved. It's because the total momentum equals 0. The second trial, momentum is negative 0.27 versus positive 0.23. There's a slight difference. Well, there is some difference. This one has the biggest difference. The third trial, we have negative 0.28 versus positive 0.27. Small difference. Momentum is pretty much conserved if we treat it as a negative. Fourth trial, we have negative 0.289 versus positive 0.28. Again, small difference. Fifth trial, we have negative 0.30 versus positive 0.28. Still rather small difference. Okay. So if we treat momentum as a vector and the opposite direction is negative, then we have a conservation of momentum. If we treat both as a positive, according to draft science, as it must be, because momentum is energy, we always have an increase. The momentum always keeps increasing and increasing, and therefore we always have more energy and energy, even though we always have the same spring constant, the same force that the spring releases. So yeah, again, it's pretty significant that the momentum here and momentum here are pretty much the same, okay, and that that it is conserved when it's treated as a vector. And it's pretty significant that, once again, even though physicist Michael has already proven this in his experiment, that also this experiment provides that, according to draft science, that the momentum keeps increasing and increasing, and therefore we have free energy, and keeps just more free energy as we keep increasing the weights. This is the same kind of scenario as in physicist Michael's experiment. So if physicist Michael experiments, if his setup is broken, then this one must also be broken, but I don't think so. It must be very significant. And so I've done 2 more analysis videos, and they also produce these kinds of this situation. And so if that's wrong, then this one must be wrong, and then the other 2 must be wrong. So it must all be wrong, and that would be very coincidental, which I don't think that's realistic. All right, so that's it for now. See you in the next one.